My name's Richard Ozaki. I'm a technical consultant for Flow EFD and other CFD products here at Siemens Digital Industries Software. And today we're going to be talking about a product called SimCenter Flow EFD and specifically some of the meshing capabilities in the tool. So we'll quickly cover what Flow EFD is if any of you are not familiar with the tool. We'll talk about what mesh is and how it affects results, how to actually generate a Flow EFD mesh, customizing and tailoring your mesh to your specific application, using something called solution adaptive refinement, which is an advanced technique to improve mesh quality based on the results that are generated. And then finally, we'll touch on generating mesh independent results using the tool as well. And these are very common activities that any simulation expert or analyst has to perform, is making sure that your results are not dependent on mesh and you've got a good mesh that will give you decent results in an acceptable amount of time with the computer resources that you have. Okay, so very quickly, Flow EFD. This is a CAD embedded CFD tool for designers. What does that mean? So there are several different types of CFD tool out there, but this one is really designed to be utilized and leveraged by CAD designers. Okay, so it's a general purpose 3D CFD tool, not specific to any specific industry. Anywhere where you've got fluid flow or heat transfer, Flow EFD can potentially be used to solve your flow and heat problems. It's very accurate. It's been on the market for about 18 years now, so it's very well established. There's a lot of customers out there using this tool, and there's a few different versions available depending on what sort of CAD system that you use. So we obviously support the Siemens CAD systems, NX, Solid Edge, but also some competitive tools as well, so SolidWorks, Creo, and CATIA. If you maybe have more than one CAD system within your company, you can leverage Flow EFD within those as well. So what are some of the capabilities? Well, Flow EFD can be used in a wide variety of different applications. So we can see here like mixing, we can do electronics cooling, aerodynamics and flow problems in external analysis type conditions. We can do rotating equipment for things like pumps and fans. We can do combustion, radiation, aerodynamic heating, even free surface models now as well. So really a very well established general purpose 3D CFD tool, again, aimed at the designer rather than the analyst. So we're really trying to democratize this tool and get regular CAD users, Solid Edge and NX users, to be able to perform the analysis rather than having to go to that analysis team and wait for results to come back. So just a quick video of it in action. So here we have flow through a pump in Solid Edge. So the nice thing about being CAD embedded is that you can make changes really quickly. So let's, for example, make a synchronous change on this valve. We're going to change the angle on the outlet of the valve. So let's just rotate that through an arbitrary angle, maybe about 45 degrees. There's our updated geometry, and then our analysis will instantaneously keep up with that geometry. So there's a lot of benefits to being CAD embedded, such as being able to utilize that parametric CAD data and make changes really quickly. Here's another example. So let me just click play. So here's a heatsink that we're designing. So this is an LED streetlight type example. So we have a heatsink, an aluminum die-cast heatsink, and rather than just going with the base case design, we can start to do design exploration. And again, because we're CAD embedded, we can push, pull surfaces, we can control pattern parameters, we can vary the different heatsink fins to achieve the most optimal cooling for our particular application and within the constraints, the packaging constraints of the heatsink, the allowable sizes. So it really allows you to do that what-if study and optimize your design for performance and being able to do that quickly within your CAD system. So today we're going to be talking about mesh. Now in Flow EFD, there's three different types of mesh. Okay, so there's fluid, solid, and what's called fluid solid interface cells. A little bit painful. They used to be called partial cells, but fluid cells are completely within the fluid region. Solid are completely within the solid region. Those are fairly easy to understand, but there's always something called a fluid solid interface cell between them, right? So here's a fluid, here's a solid. There's always this interface cell, and that's where the interesting stuff happens in FlowEFD, because that's where the solid and the fluid touch each other, and that's where the convective heat transfer happens. That's where the boundary layer forms in the model, and that's really the core behind the FlowEFD technology, is being able to use these fluid-solid interface cells. Now in FlowEFD, we use something called a immersed boundary Cartesian mesh. So what that means is that we create these cuboidal grid cells in the model, and then to refine the grid cells, we split that using octree refinement. What does that mean? So we take a single large grid cell like this, split that into 4, right? It's actually 8 in 3D, so that's your octree. Split that into 4 again, 4 again, 4 again. So it's a very structured way of increasing mesh density, and it's very easy to add or remove grid cells if they're required or not required, okay? And one of the main rules of FlowEFD is that the neighboring cells cannot vary by more than 1 level. What do I mean by that? Well, there's various different level sizes. There's level 0, level 1, level 2, level 3, and we'll see this when we come to the demonstration, but you'll see that you can't go from a tiny grid cell to a huge one. You have to go through this splitting ratio to get down to these small grid cells, this 2:1, 2:1, 2:1 ratio, and also the aspect ratio of the grid cells are maintained as well as you go smaller and smaller. Now, within solid cells, FlowEFD can have multiple materials, up to 36. Okay, so when it's a conduction-only problem, the solid bodies defined by the CAD geometry are very well defined, and you don't need to increase the mesh density so much when you're just concerned with conduction. Okay, convection is a different problem, or flow-based cells are a different issue, but for conduction, you can have a lot of materials in a single grid cell. Like this one over here has got 4 materials based on the geometry that's been created, for example. Now, fluid-solid interface cells, or what they used to be called partial cells, now they have something called control volumes within them. So if we have a look at this cell here, for example, where my mouse is, you have a fluid region, solid region, and a fluid region. Okay, so this is what we call a 3 control volume cell. Okay, the recommendation is to not have more than 4 control volumes. This one here, this cell here, this has got 1, 2, 3, 4, 5. I wouldn't be too happy running this this grid cell without further refinement. This one here has got 3, 1, 2, 3 grids control volumes. So you know, and we recommend no more than 2 control volumes per partial cell if critical, and 2 is the lowest that you can go down to in terms of control volumes. So in terms of a heat sink, which is what we have on the screen here, you want to have at least 4 cells, or around 4 cells within the heatsink fin gap. So that means at least 2 partial cells and 2 fluid cells. So how do we achieve that? Well, we can increase the mesh density. Remember the octree splitting that's going on. So we take that grid cell, we split it into 4 again. That increases the number of control volumes. So that cell previously now has been turned into like a 3 control volume cell with a fluid cell right next to it. We can keep refining and keep refining to increase the mesh resolution and also the result resolution. Okay, so here we have a fluid-solid interface cell count comparison, where as you increase the mesh density, the image gets sharper, the resolution gets better. We're getting more accurate simulation results at the cost of higher computer resources and higher solve times. So there's always a trade-off between mesh resolution and computer and time resources available to you. Okay, so let's talk about actually refining the mesh. So we can use something called local initial meshes in FlowEFD to increase mesh density. So we can apply a local initial mesh on a surface, an edge, a vertex, or a CAD body. And by clicking on these parts in Solid Edge or NX, we can increase the mesh density using the leveling system. Okay, so I'm going to skip over that one. We can also use bodies, arbitrary bodies, cuboids, cylinders, or spheres to actually increase the mesh density wherever we want, and we can size those and place those wherever we wish. Okay, and we also have something called inflation in the model as well, which will increase the mesh density as you move away from a body, which is particularly useful for external aerodynamics types cases. So what I want to do is just kind of jump into the software and show you a little bit of that. So first of all, I wanted to show you in the NX version. So this is a quick release fluid coupling. You probably use one of these at least once a week. Okay, whenever you fill your car up at the gas station, this is a breakaway valve. So if you leave your gas nozzle inserted in your car and you drive away, this is the device that will break away and keep the gasoline from spilling everywhere, right? So there's a male part, there's a female part, they connect together, and they're designed to break away and quick release with minimal fluid loss. And if you're a designer designing something like this, you want to make sure that you're getting sufficient flow through your valve whilst minimizing the pressure loss in the system. What's the actual upstream pressure required to overcome this resistance that this valve is causing to your fluid system? Okay, so let's have a look at the Flow EFD mesh first of all. So I'm just going to go normal to the screen and visualize what we call the base mesh. So the base mesh is overlaid on the screen, and these are level 0 grid cells, and I've manually set these to 2 millimeters in size each. Okay, so if I just rotate that in 3D, you can see that there are, in all three directions, we've got these 2 millimeter grid cells, and that's important to keep those, keep these values as uniform as possible. So we've got that nice aspect ratio of 1 to 1 to 1. Okay, now, like I mentioned, this is your level 0 grid cells. Now, to increase the refinement level, we can actually preview that, and it's struggling to see that. So let's go to display refinement level. Okay, so you can see, here's my level 0 grid cells. As I move this slider bar up, look how they split into 4 again. All right, so there's, if we look at this one, for example, or this one, level 1, level 2, level 3, 4. So you have this exponential increase in grid count as you go down and closer and closer. So all the way up to a maximum of level 9. So again, if we zoom out, it looks completely black now because the grid cells are so small. So you can control the mesh density using these slider bars to increase or decrease the mesh resolution based on your requirements. Now let me just cancel that and actually show you what the generated mesh looks like. So here, based on automatic settings, the software has created the grid and they're colored by this refinement level, right? So your level 0, level 1, level 2. And I've stopped the mesh from increasing beyond level 2. And if we now start to use local initial meshes, which are up here, you can see that you have this local mesh option. I'm going to turn on a couple of local meshes that I've created previously. So one of them, for example, is a cylindrical local mesh region. Yeah, so if I go into the properties of this, it's just you don't have to create an NX part or anything like that. It's just a cylinder, which I can click and drag, make larger. I can make this taller. So you can create these arbitrary volumes, position them, and then tell the software that you want increased mesh resolution in those areas. And I'm going to mesh the model real quick. This just takes a couple of seconds. It's a pretty small model, so it's just preparing the model now. It's mesh refining. I'll get a feel for what the total grid count on this model is going to be. I know this is pretty low, but yeah, this local mesh is a way of increasing it from the base that we saw just a second ago. So we'll just let this finish capturing. Should just take a few seconds here. And then look, we can see we've got 350,000 grid cells total. Okay, so that's interesting. That's important information for me because that will tell me, right, do I have enough RAM in my machine to solve that? Absolutely, 350 is next to nothing. So that's no problem whatsoever. But now if we look, and let me just auto range this. All right, so now if we look, we've got much finer, smaller grid cells in these small gaps, but only within that region that I specified, right? So it hasn't put them everywhere. I've also got finer mesh around this threaded portion and this valve over here. So you can control, you can apply base grid and then local initial meshes within the model to increase in certain critical areas that you yourself have defined in the model. Okay, so let's go back to the PowerPoint, and we're going to talk about solution adaptive meshing next. So this is a very advanced feature available to everyone. You don't need an extra license or anything like that. It comes with the base flow EFD. But what this does is it will increase the mesh density based on the actual solution. So if you're finding that there are flow separation zones or high turbulence zones or areas of high parameter gradient, like temperature gradient or velocity gradient, the software will recognize that and realize, I need better resolution here because there's too much of a change within this cell. It will then split that cell and split it again and split it again until the gradient parameters have been satisfied. Okay, so let's look at an example. So here's a filter. Okay, so we've got flow going from right to left. It goes through this screen. It's a hydraulic filter. It's designed to remove larger particulate matter from hydraulic fluid. Okay, here's our flow region. We're taking advantage of 1/4 symmetry. Okay, and here's the mesh in the top left that I have defined manually. So I've added a local mesh around the filter element because there's lots of little holes there. Okay, but then you can see the subsequent mesh refinements that have occurred because of the solution adaptive meshing. So not only has it put extra mesh around the actual element itself, but also here on these corners, for example, where you've got flow separating, potentially recirculating. Okay, and then on the downstream area as well. And what does that do to the results? Well, a bit like a digital picture, the more grid cells we have, the finer the image or the resolution is going to be. The more pixels we have, the better the resolution is going to be, but the more space it takes up on your disk, right? So you can see as we increase the mesh density, we start to see finer features in the flow. We start to see these little jets forming, and that's a direct result of that extra grid around the filter element there. Okay, and what we're really looking to do is achieve a mesh independent result. So that means we need to manually increase the mesh density in the model until the results stop changing. So here's the delta P, the pressure loss through that filter against an increasing mesh count. All right, so here's our first one with a really coarse mesh. So how do we know that result's any good? It's giving me, what's that, 4.2 bar of pressure loss. Is that the right answer? I don't know. Let's double the mesh count and see. Well, when I doubled it, the result dropped 6%. That was nowhere near good enough. Okay, let's double it again. The results dropped 9%. Yeah, that result wasn't good enough. If I double it again, it only drops 1% this time. So probably this was okay. And if I double it again, it only changes 0.5%. So this is a test that you need to manually do to understand if your grid that you've applied is any good. And FlowEFD tries to make that as easy as possible for you. And I'll give you another demonstration. So here we have an aircraft. This time we're in Solid Edge 2020. Okay, FlowEFD works exactly the same way. And let's have a look at the mesh that's been applied. So here we can see the aircraft mesh. As I zoom out, you can see the size of the computational domain. And by the way, we are taking advantage of half symmetry on this aircraft. Right? So we're just doing 1/2. That reduces our mesh by half. Let me just hide that again. But you can see the aircraft. And one important thing just to note is that we do have something called aspect ratio skewing. So closer to the vehicle, these dark blue grid cells are smaller, but in the far field, they're much larger. So you can stretch and skew the grid cells to put larger ones in the far field where there's not actually that much flow going on, especially in front of the aircraft. Okay, so there's the mesh on this vehicle. And I've used, have I used? No, I haven't. That's going to be the next one. So let me just unload this one and jump over to my other project, which just takes a couple of minutes to mesh. So I've already pre-meshed it. But this time I've used something called equidistant refinement. What is that? So equidistant refinement allows you to create nested regions of increased mesh density. Okay, so I've gone 100 millimeters, 750, and 2000 millimeters away from the body. Okay, so if we have a look at the actual mesh, and let's visualize that. Okay, so it's taken the outer shape of the vehicle, and look, this is the first 100 millimeters, 750, and then 2000 as you zoom away from the aircraft. This is obviously not full size. This is just like a model. But this just stops those very large grid cells from sort of, abruptly changing into these smaller ones. You still have to go down in the levels, but you're creating this buffer around the aircraft to sort of increase the mesh density gradually. And in FlowEFD we can visualize this. Let's as I move it through, you'll notice that it's the same on the wing profile as well as I move away from the aircraft. And if we look in the top direction, you can see that's very much the case. We do have a 3D mesh on here, and if we look cutting through the aircraft as well, let me just cut through the wing. You still have that buffer, the shape of the aircraft all the way around the vehicle. All right, so now let's have a look at the actual solution adaptive meshing. So I'm going to run this live now. So let's run this calculation. And the nice thing about FlowEFD is that we can actually preview the simulation as it's actually solving. Okay, so it's just preparing the model now, and we are going to start solving as soon as this clicks over to one iteration. We'll start to see some results. Okay, so I'm plotting velocity alongside the mesh, and as the iterations count up, we can visualize the forces. Okay, so this is the amount of drag and lift that is being created by this vehicle. Let me just tile these real quick and come over here, something like that. Okay, so these are pretty much steadied out. I'm not going to run it all the way through to convergence, but what I am going to do is force a mesh refinement. So let's just hit the refine button, which is this little hammer icon up here in the toolbar, and that will stop the calculation at 28 iterations. We can see that our base mesh was at 81,000, really, really low. And then the software is going to automatically, based on the results, increase the mesh density. So you can see it's mesh capturing. And then it's going to just carry on from where it left off. It will interpolate the results and carry on. So as soon as this turns to 29 iterations, we'll see an increased mesh density. And I suspect that the drag and the lift values that are being generated will change as well. So it's just preparing for the calculation now. Let's have a look at this one. I think that's the same graph, so we don't need that. So you can see, look, it's jumped up to 249,000. Okay, so we go, oh, did that update itself? Let's clone that one. And let me just create that again. Let's just create that preview on the top plane. Let's look at the velocity and also the mesh. Maybe that was in the wrong plane, so apologies. Let me just grab the correct plane in the model, which is going to be this one is the front. Let's look at velocity, 2000, show the mesh. Just needs to do a couple of iterations for it to catch up. But what we would see when this preview actually catches up is that the mesh will be refined around the wings, around the separation areas, in the wake zone as well. So as the aircraft leaves a lot of wake in the background, we will see that increased mesh in that area to capture things like eddies, vortices, and separation. So what this comes down to is the fact that the software you can start really coarse. Okay, so let me just increase this. Okay, so here's an example of what I was talking about. So the mesh wasn't refined back here. Okay, the software has done this automatically around the actual surface of the aircraft. It's increased as well. Okay, and along the tail region as well. So the software you can start coarse and then let the software do the hard work. Let it work out where it needs extra mesh. You don't need to have like a pre-knowledge of what the solution is. You can just let the software do the hard work and increase the mesh density only in areas, critical areas within the model. Okay, and you can do this multiple times. You can refine constantly, or you can refine at specific intervals, or maybe when certain parameters reach certain predefined thresholds. Okay, so very powerful. You can see around the engine nacelle, things like that. Okay, so that's got to the top of the 30 minutes that we had for this session. So at this point, I think I'd like to take any questions that have been put in the chat box. So Rebecca, do we have any questions at the moment?
Hi, Richard. Well, it looked like you did a great job covering everything because we don't have any questions at this time. So I think we could just move on to the closing slides.
Okay, what I will say is, if you like what you see or you'd like to try FlowEFD, please get in touch with Saratech. They can set you up with an evaluation, or you can try the software out and see what you think.
Thanks for checking out our channel. If you like what you saw, make sure to like and subscribe down below so you don't miss out on any new videos. Follow us on LinkedIn, Facebook, and Twitter for the latest engineering news and information. And to see all of our upcoming events, please visit our website at saratech.com/events.